Hello. Now we are going to have a look at Venn diagrams involving three sets. Now nothing really changes here. It's just that because we have three sets involved now, in this case A, B, and C, we have more options for some of our questions. We have our operations can be acting on more than two things, and as a result, the questions can look more complicated, but the ideas remain identical. So we'll just get used to our language, and we're also going to discuss the idea of the associative property of numbers and sets. So we start off with our example here. The universe for this question, all of the elements that we could possibly deal with in the question are described by x, where x is greater than or equal to 1 and less than 10, where x is a natural number. A is the set 2, 3, and 7. We have our curly brackets. We have a comma in between each element, B and C. First thing we need to do is clearly write out the elements of U. So we need to translate from this description of the set into clearly listing out all of the elements of the set. So we open up a curly bracket, and what have we got here? We're going from 1 up to less than 10. So our group can include 1 because x is greater than or equal to 1, but we cannot include 10 because x is less than 10. So 10 would not be one of our elements. So we have 1, 2, 3, 4, 5, 6, 7, all with commas in between. And then we close our curly bracket. And we could do a slightly better curly bracket than that. So again, our curly brackets, we have to show that there's either a little loop or a kick out in the middle of our bracket to make sure we get our marks for our notation. Now we need to fill in our Venn diagram. And just as we would have done with Venn diagrams that have two sets in them, we always start in the middle. And in this case, there is an even more middle point than just the intersection of two sets. We look for what's in the intersection of all three. Is there something that is an element to all three of our sets A, B, and C? Obviously, everything's an element to the universe. That's how a universe works. But we want to know, is there something that's an element common to all three of our sets, the intersection of all three of our sets? So we go through our lists, and I can see, well, 1 is in B and C, but it's not in A. 2 isn't in B. 3 is in A and B, but isn't in C. 7 is in all three. So I have 7 is an element in all three sets, and that's how we run through. We put down the number 7, and because that's the element 7, and we're not saying that there's 7 elements in that set, we have to put our dot next to our number. Those dots again tell us the difference between, are we dealing with the cardinal number? Is there 7 elements in this set? Or are we dealing with the element 7? Is 7 a member of this group? So we mean a member of the group, so we put a dot so that we know we're talking about the element, the member of the group. Then we look for the intersection of two of the sets each. So is there anything that's common to A and B but isn't in C? So 2 is in A but not in B. 3 is in A and B. So 3 is in A and B, but it's not in C, so I'm going to put it there. So 3 goes in the intersection of A and B, but it doesn't go in here because it's not in C. So this is the overlap of A and B, but not inside the set of C. Now, is there any overlap between A and C that isn't already covered by our 7? So A and C, there's no 2 in C, and the other ones are already accounted for, so there's no overlap here. So is there any overlap between B and C? We have a 1 is an overlap, but the number 1 is an overlap between B and C. Is there any other ones? So 4, no. 5, no. And 7's already used. So I apologize, I have that in the wrong place. So 1 is in the overlap of B and C, but it obviously isn't going to go in here because 1 is not in the circle for A. So continuing on now, we fill in the bits that are just in A, only in B, only in C, or just in B and C. So 2 is in this part of A, it's only in A, it's not in any of the other two sets. And B has 4 and 5 that are only in B. Mark them off as we have them because our list is getting quite big. And then C has the element 8 is the only thing in there. So finally then we say, well, we've got all of our stuff in A, B, and C sorted, and there's nothing in this part of the set, but that's okay, we just leave it blank. Sometimes in the exam, I will just note, sometimes in the exam you can see it shaded out like that. There's no requirement to do that when you are writing it, and I am not going to particularly encourage you to do so, but in the exam you can see it shaded out like that when it is an empty set. Now let's look for what's in our universe but not covered by any of our 3 subsets of the universe, A, B, and C. So 1 has been used, 2 has been used, 3 has been used, 4 has been used, 5 has been used, 6 has not been used, 7 has been used, 8 has been used, 9 has not been used. So we go down through, underline all of the ones that have been used up, and then we write down the ones that are in the universe but aren't in A, B, or C. So we can see, as we always have, we start from the center, we work our way out in the intersections, and we write what's only in A, B, and C, and then we find the remaining part that is only in the universe. And if we start from that center point and work our way out, even as the questions get more advanced, more complicated, we will have that structure, and that will help guide us what to do, even when the questions get more difficult than this. So now, let's go through some questions. We have A intersection B. So in this case, we're asked to list the elements of A intersection B. There's no cardinal number or anything listed here. So we open up our curly bracket for listing our elements, and we want A intersection B. Well, that'll be 3 and 7. Both 3 and 7 are in A and B. So for intersection, we're looking for the stuff that's in both A and B, and 3 and 7 are both in there. The fact that 7 is also in the set C is irrelevant. What we're looking at is it is inside the circle A and inside the circle B. And if it's in both of those, we're going to include it. So as we're dealing with 3 sets, we now need to be much more careful. We don't care whether it's in C in this case. We only care about whether it's in A and B. So the fact that it looks a little bit cordoned off here is irrelevant. We simply look for what meets this description, what's in both A and in B. Now, A union C. We're listing elements, so we open up a curly bracket. A union C, so everything in A or C or both. So 2, 3, 7, 1, and 8. And again, if it's in B, we don't mind. That has no effect on what we're doing right now. We're only interested in, is it in A or C or both? And we have all of them listed now. And now we can see this can get a little bit more complicated, but we do this step by step and it isn't too bad. So A union C, so A union C, anything in A or C or both, but not B. So we're going to exclude anything that's in B. So we know that we're looking for anything in A or C or both, but not anything in B. Well, what's left there? That's going to be 2 and 8. So open up a curly bracket because we're listing elements, and 2 and 8. A union B union C, so the U in between other 2 sets or several sets means union as opposed to U by itself, that means universe. So A union B union C, complement. So A union B union C means everything that's in A or B or C or all of them. So everything inside all of our circles. And then we want complement of that would mean not that, effectively. Everything but that. So that just leaves us with 6 and 9. So open up our curly brackets. And that's going to be 6 and 9. B intersection A intersection C. Now the order of A, B, and C don't matter for intersection or for union because we understand what those things mean, and the order that we say them in wouldn't matter in those cases. So A or B intersection A, B intersection A would be 3 and 7. Intersection C would be what's the intersection, what's the overlap of this set here with C? Well, that's just going to be the element 7. And that, I did not notice till now, should not be there. Cardinal number of B not A. So B but not A is going to leave us with 4, 5, and 1. So that's 3 elements. And there's no curly brackets there because it's just the number 3. There are 1, 2, 3 things that meet that description. Cardinal number of A union C union B. So the order of our union doesn't really matter. So we're just finding out all of the stuff that's in A, C, and B, or both. So 1, 2, 3, 4, 5, 6, 7. There are 7 things there. Cardinal number, it's not an element, it's the number 7, so I don't have to put in curly brackets. And B not A intersection C. So B, but not A intersection C. Well, let's deal with the bit in brackets first. So A intersection C is just going to be the element 7, so not including that bit, but everything in B, but not that bit. So 3, 4, 5, and 1. And this is listing out the elements. So curly bracket, 3, 4, 5, and 1. Now, I've mentioned a few times as we're doing this that the order of operations doesn't matter for union or intersection. So let's have a look at the formal language around where the order of an operation doesn't matter. So the order of operations doesn't matter as an example for addition. So if I did 4 plus 5 plus 6 or 4 plus 5 plus 6, it wouldn't matter what order I did them in, I'd get 15 in either case. So addition is associative. The order in which I do this operation doesn't matter. Which two I add together first makes no difference. But that's not always the case. If we had 4 divided by 5, then divided by 6, or 4 divided by 5 divided by 6, that would result in quite a different answer. So the order of operations does matter for division. So before we dealt with commutative operations, where the order in which we wrote our terms didn't matter, and now we're talking about associative, where the order in which we do our operations doesn't matter. So division is not associative because the order in which we do our operations does matter. Now, in terms of sets language, A not B knotted with B not C is not the same thing as A not B knotted with C. So B not C, so B but not C would be this part of B. Knotted with A would mean that it's A but not this bit of B. So that would include the intersection down here. But if we had A not B would be all of this bit, what we had before, but not C, which would exclude that. And you can see that these two shaded areas are not the same. This little intersection bit here is missing in the second example. So they're not the same. They're not talking about the same region of our Venn diagram, so they're not equal to each other. So the order in which we do set difference matters. But we can see for union and intersection that it wouldn't matter which way we argued our union, whether we did the union of A with B union C or the other way around. It works out identically in each case. As a result, we say that union and intersection are associative because the order of operations doesn't matter for them. That's what we need for associative and for our Venn diagrams with 3 sets.